A very good afternoon to one and all from India. I, on behalf of the entire organizing committee of IBWCST 2022, welcome you all to the penultimate day of this virtual international workshop. We are also immensely pleased to see young researchers and dignitaries from various institutions actively participating in all the sessions. Once again, I welcome you all to the second lecture of today's session. During morning session, we have witnessed an elaborate lecture delivered by Dr. Wiwit Suryanto from UGM Indonesia on crustal anisotropy of Sumatra from harmonic decomposition of receiver function. And for this session, we have with us Professor Sagarika Mukhopadhyay ma'am from IIT Roorkee as a keynote speaker. Ma'am will be delivering her talk on the topic 3D seismic velocity structure of the lithosphere and its geodynamic implications for the Western Himalayas, Western Himalayan syntaxis, and Pamir Hindu Kush region. Madam, we wholeheartedly welcome you to the session of IBWC 2022. We are also privileged to have with us today Professor Jaya Kyle, ex-Deputy Director General of Geological Survey of India as the session chairperson, and Dr. Debojit Hazarika from Wadia Institute of Himalayan Geology, Dehradun as the session co-chairpersons. Now, may I request the Honorable Session Chairperson, Professor Jaya Kyle sir, to provide his initial remark. Over to Professor Kyle sir.
Thank you, Navjyoti. Thank you so much. I think nothing to say except that Professor Sagarika Mukhopadhyay, we are collaborating since last more than 2 decades, or about 3 decades. And she is one of the authorities in seismic tomography studies in India. We have done a lot of collaborative work for large earthquakes like Bhuj and Kilari and all that. But today, also for Northeast India, we have made a Indo-collaborative, Indo-Russian project together. So, but today we are going to listen to her on the seismic structure in one of the or the most complicated zone in the Western Himalaya syntaxis and Pamir zone. There is a lot of debates on the subducting structure or Indian bed tipping structure, double subduction, all these things, very complicated zone. And today that topic is chosen by Professor Mukhopadhyay, and she is going to enlighten us this particular topic. So thank you, Mrs. Mukhopadhyay, for kindly accepting our humble invitation to present you this very important lecture on this topic. I think without lengthening fast, I would like to appreciate and again thank Professor Sagarika Mukhopadhyay for this very important topic. Over to Anchor, and we all look forward to listening to Professor Mukhopadhyay.
Thank you so much, sir. Now, may I request Dr. Debojit Hazarika, sir, to say a few words. Over to Dr. Hazarika.
Very good afternoon to all of you, and respected Professor Sagarika ma'am. And she is a well-known seismologist of our country, and who is expert in the passive seismology. We have read many of her papers on the local earthquake tomography. A very excellent piece of work she has done it, and we are fortunate that we are able to listen to her lecture today. And I think all the youngsters, and including all of us, will be very much benefited from her lecture. On behalf of the third international virtual workshop on the global seismology and tectonics, I would like to welcome you, madam, to this workshop. And I request to proceed. It is over to the anchor.
Thank you. Before moving ahead, I would like to request Dr. Sinmay Raskowar, who is a scientist at Geoscience and Technology Division, CSR, NEIST, to read out an illuminating biodata of Professor Sagarika Mukhopadhyay. Over to Dr. Raskowar.
Thank you, Mr. Novosity. A very good afternoon to one and all present in this session of IVWGST 2022. It's an honor and privilege to introduce our keynote speaker of this session, Professor Sagarika Mukhopadhyay from Indian Institute of Technology, Roorkee, India. Although she is well-known seismologist in India and abroad, I am going to read out a concise biodata of Madam to our participants. Professor Sagarika Mukhopadhyay is serving as a professor in the Department of Earth Sciences, Indian Institute of Technology, Roorkee, India. She did her master's in exploration geophysics from IIT Kharagpur and MS in geophysics from State University of New York, USA. She has completed her PhD degree in seismology from University of Roorkee, India. Professor Mukhopadhyay was a recipient of Koch's visiting professor's position and Lowenstein Fellowship by Stanford University in the year 2018. Her field of research includes seismic table-time tomography, surface wave analysis, receiver function analysis, attenuation and anisotropic characteristics of the Earth, seismotectonics, seismic hazard microzonation, near-surface study using seismic wave, etc. She has authored more than 100 high-quality research articles, book chapters, and conference papers published in journals of national and international repute. Professor Mukhopadhyay has successfully completed many national and international sponsored research projects dealing with seismic hazard and risk analysis, as well as consultancy projects for seismic hazard assessment in India. She is a member of various professional bodies like Indian Society of Earthquake Technology, Indian Geological Congress, Society of Exploration Geophysicists, American Geophysical Union, etc. With this brief introduction, now may I request Professor Sagarika Mukhopadhyay, Madam, to take over the digital forum and enlighten us with her lecture. Over to you, Madam.
Thank you very much, and a good afternoon to everybody. Thank you, Professor J.R. Kayal, for giving a beautiful introduction about me. Thank you, Dr. Devajita Hajarika. Without you people, I will not be able to do much work. And thank you, Dr. Shantanu Barua, for inviting me for this very important international conference. And good afternoon to, if I don't mention your name, please don't assume that I've forgotten you. So good afternoon, everybody, all the young colleagues, all the students from NEIST Jorhat. Today, I'm basically going to present our work done by my research team in my lab. Essentially, this work is pertaining to the PhD work of one of my students, Dr. Javed Rauf. So, what I'm going to present is basically a crustal and upper mantle image of Western Himalayas, Western Himalayan syntaxis and Pamir Hindu Kush region based on travel time tomography. So basically this is a brief introduction of the tectonic domain of the whole of the Himalayas and surrounding region. We all know of this figure very well, but in order to make a continuation of the presentation, I would like to give a very brief introduction about the tectonic processes. India collided with Eurasia about 56 million years ago, resulting in the one of the highest mountain chain at present these days, that is the Himalayas and the Tibetan Plateau. And the Himalayas, we know that there are various thrust systems which separate different type of rock types, like MFT, main frontal thrust, that separates the Indo-Gangetic plain from the Shivalik Himalayas, and then the MBT, main boundary thrust, that separates the Shivalik Himalayas from the lower Himalayas, metamorphic, sedimentary and metasedimentary rocks, and then the main central thrust that separates the lower Himalayas from the higher Himalayan crystallines. Then after that we have the South Tibetan detachment surface, that is essentially that separates the higher Himalayas from the Tibetan Himalayas. I think it's not visible here. And then the Indo-Socha zone, which is supposed to be the zone along which the two plates collided. On the eastern side, we have the eastern and western edge of this collision zone is very, very complicated. I have already published papers on the central Himalayan tomography and then the eastern Himalaya, northeast Indian and Indo-Burma ranges tomography. So on the eastern side, we have the Indo-Burma ranges, the Sagaing fault. So around the Indo-Burma ranges, India, we find subducted Indian plate below the Indo-Burma ranges, and Eastern Himalayan syntaxis is a very, very complicated area, and based on surface wave tomography, my students have found that there is a very drastic change in the crustal thickness around this region. But today I'll be concentrating on the Western Himalayas. I hope you can see the pointer that I have over here. Can you see it?
Yes.
Hello?
Yes, ma'am.
Yes,
Okay.
very clear. Yeah.
Okay.
Pointer is visible.
Okay, thank you very much. So then we have the Karakoram fault and the Western Himalayan syntaxis, main mantle thrust, and then the Pamir, the Western syntaxis, the salt ranges in the Pakistan region, and then you have the Pamir, Hindu Kush, Chaman fault, Herat fault, and Pamir frontal thrust, etc. There are many, many more faults and thrusts in this area. In order to keep the figure simple, kind of skip them. So what is, now I'll be concentrating on this part of the area. Why I'll do that? Why not the entire area? That I'll discuss shortly. So very briefly, the geological features that I have already discussed. We have the higher Himalayan crystallines, higher Himalayan lithogranites you see here, lesser Himalayas, and then Proterozoic metamorphic basements, Indo-Socha zone and related rocks over here. We have the Kohistan Ladakh Arc and Ganges batholiths, and Indo-Gangetic plains, of course, and some part of Tethys Himalayan rocks over here. So this is a geology based on, I've taken it from Guillot et al.'s paper. Now, what happens before we continue? We should have a very brief discussion about how all these rocks form. So what happened is that here we have a figure from Jagals et al. 2015 that shows the plate motion. Here we have the Indian plate at 90 million years ago, and then 80 million years ago, and then we have it around 50 million years ago. Basically, this should be closer. Here there is a subduction front that we see, and then 40 million years ago we see that they have already closed. Basically around 50 to 60 million years ago the closure occurred. Present day scenario, what we find is that we have the Trans-Tethyan intraoceanic system, which was active after 80 million years. We find them all around the Indian subcontinent, and the yellow rocks are the arc rocks related to the Cretaceous subduction system, and the white rocks we see here and here, they are associated with subduction that terminated before 80 million years. Right. Keeping this in mind, let us continue with our travel time tomography. So basically, this shows the green dot shows the earthquakes epicenters, and the red inverted triangles show the stations from which the data was taken. We had all this data together, but we didn't have any tomographic software that could handle the local and regional tomography. I'm not talking about teleseismic tomography here. Local and regional earthquake data, using local and regional earthquake data that could handle such a big area together. So we decided to divide it into three parts, three overlapping parts, part 1, 2, and 3. And the tomography was done for these three parts separately. And of course, over the overlapping parts, we compared the results and we found that they match quite well. So we are satisfied that the tomography work was working quite well, even when we are using different data sets. So now let us come to the area of study, which is shown here. Basically between about 66 to, I'll say, 80 to 83, or maybe 67 to 82, this longitude, and about say 28 to about 40-41 degree north latitude. This is our area of study. Here on the topographic map, a few of the tectonic features are shown, and basically this is shown with earthquakes with magnitude greater than 6 are superposed on this. Please note, these are earthquakes since 1850, which means that many of them are basically supposed location based on the intensity map, and the magnitudes that are shown, especially like magnitude 8 with the years shown, 1896, 1895, and 1505. These magnitudes are intensity converted to magnitude, not the instrumentally determined magnitude scale. So we see that here a lot of earthquakes, especially with magnitude 6 to 7 and 7 to 8 occurs, and there's a concentration of such large magnitude earthquakes in the Hindu Kush region, right? So what we see next is the data that was used for this tomographic analysis. Here only the earthquake data are shown. The color coding is done for that focal depth. So the sizes were not mentioned here, what is the magnitude of the earthquake. But what we notice is that, of course, you may say that why we don't have that many earthquakes over here and here. This is the Delhi Hardwar Ridge, because this is very intensely instrumentalized. A lot of seismic stations are over here. But however, please note there are a lot of, so as a consequence, we get to see a lot of earthquakes over here. But of course, it is also well known that this area is seismically active. But what I wanted to say is that please note that the green colored dots, they are more in number along Delhi Hardwar Ridge as well as the Western Himalayan region, which is part of our area of study, right? So basically, mostly we see shallow focus earthquakes in this region, in the Western Himalayas and Delhi Hardwar region. And we also notice that this red and black colors, which red color is 100 to 150 and black color is for 150 to 350 kilometer depth. So intermediate focus earthquakes are more frequent in the Pamir and Hindu Kush region, with a little bit of it occurring along the Altintat fault, right? So we have a near the Pamir frontal thrust, which is parallel to Pamir frontal thrust. We also see earthquakes occurring along the salt ranges over here. So these are the data that we had, the P and S phase data of these earthquakes. The earthquakes that occurred between 1960 to 2016. Why 2016? Because my student submitted in 2017. So he could take data only up to 2016 for this analysis. Now here we show all the earthquake data in as green dots and the stations from which the data was taken as red inverted triangles. Above and along with that, there are some yellow colored lines which show the lines along which we have taken profiles to see how the velocity varies with depth. So data source is IMD and DMN, which is Department of Mining from Nepal, and ISC. Now, ISC, the data was contributed by the countries like Afghanistan, Pakistan, Kyrgyzstan, Kazakhstan, and China. So we had 2,80,785 peaks, out of which 1,72,497 P peaks and 1,08,222 S peaks from 16,903 events recorded in 237 stations. So why am I number? Important to have a large volume of data. Of course, good quality is also essential. But we hope that IMD, DMN, and ISC, the peaks were reliable enough. So we did some kind of analysis to check the quality of this data because we did not pick them ourselves, okay, and then proceeded. So every earthquake that was available, we did not take their data. Basically, minimum number of phase peaks for a given earthquake for which data would were incorporated were 10. Okay. On an average, however, the number of peaks per event, per earthquake was 17 peaks. So that's about the data and the methodology. We have used a travel time tomography method called LOTUS that was developed by Professor Ivan Kolakov who is based in Novosibirsk, Russia. And this method is, and I'll just briefly mention it because it's not my method, I'm just the user. But if you're interested, you can read his papers and then you can download this software from his website. So it's an iterative least square inversion technique where simultaneously P and S arrival times from local and regional events are inverted to estimate 3D P and S wave velocity variations and also simultaneously revise or relocate the earthquakes in a newly obtained 3D.
Some problem or what?
I think some interruptions is there.
Advise that to leave the video.
Hello, can you hear me? I hear
Yes,
some
now we
noise.
can.
Yes,
now we
now
can
it is
hear you.
Yeah, there was some noise. I didn't understand what is going on. So how much did you hear before? This 3D VP and VS variation?
Yes, yes.
Okay,
3D
so
VBS, DS mix.
yeah, so step-by-step process is that first we provide an input in the arrival time data to the software and one initial 1D velocity model, and then it the software runs several iterations to find out what is called an optimum 1D velocity model. Basically, the velocity, the thicknesses, those are changed to find out an optimum 1D velocity model that can satisfies or minimizes the RMS error of the earthquake, the PNS phase data. Next, in the next phase, 3D grids are made in 4 different orientations. Why 4 different orientations? Because if your orientation is fixed, sometimes that introduces artifacts in the data. So the Professor Kolakov developed this method where he had 4 different orientations: 0 degree, 22 degree, 45 degree, and 67 degrees. And the grid, the 3D grids, the grid node separation would be based on initial ray density estimates at each location. And so for us, in the area where the ray density was good, The grid node separation was 30 kilometer in the horizontal direction, and its difference was about 10 kilometer in the vertical direction. Initially, to start the forward problem, ray tracing method is used. Here, a bending method, which was originally developed by and Tharbar in 1987, was used. And next comes the inversion, where in the software, the LSQR, the least square QR decomposition technique of Page and Saunders, developed in 1982, was used. So average, and then for each orientation of grid nodes, inversion is carried out, and then for a given grid node, the results from the 4 grid orientations are averaged out, and that is used as the input model for the next iteration, and this continues till the iteration. There's a minimum RMS cutoff criteria of the data that is met. If you are not able to hear me, Dr. Barua, please call me. I have my phone with me.
Okay. You are audible. Madam.
Okay. So residual was in this process. The inversion was carried out, and the residual reduction was 0.819 second to 0.624 second, or 23.83% of variance reduction for P wave, and 1.3449 to 1.013 second, about 24% variance reduction for S wave. Now, first thing that we have to decide is what is the most appropriate initial 1D velocity, the 1D velocity model that we should start with to carry out 3D inversion. So for the area under cover, there are many different 1D velocity models available. For example, Saiki et al., the blue cyan colored one, yellow colored is Mahesh et al. 2013, and Mukhopadhyay Sharma, this is for Kumar Garhwal Himalayas 2010, this is my student's work, and Hana and Veera Ratne 2013 for Western syntaxis, Sipal et al. 2013 for Pamir Hindu Kush area, and also AK135 Kenneth et al. 1995, that is the global spherical 1D velocity model. Then Kufner et al. 2017 for Pamir Hindu Kush region. And we have tried all these different initial models and inverted them, and the final 1D model obtained from each one of them we have compared, and the one that is giving the minimum RMS error is what we have taken as final optimized 1D reference velocity model, that's given in this green color. Please note that it's kind of coming somewhere in between. That is because the 1D velocity for Western Himalayas and that for Pamir Hindu Kush should be different, and it is kind of coming out somewhere in between. But Western Himalayas, most of the velocity models are they stop around, say, about 90 kilometers, 100 kilometers or so. So below that, what we find is that the velocity is the optimum 1D velocity model is progressing towards the ones for Pamir Hindu Kush region. This is the VS model, and this is the VP model, that is P wave velocity and S wave velocity. So this figure shows the ray path coverage map of P, and on the top panels are the P ray paths, and for the bottom panels we see the S ray paths. The ray path coverage depends on the earthquake locations and the station locations. Of course, the stations, which are all stations, have not recorded all earthquakes. So depending on that, the ray coverage is seen. So here we see that this is the 20 kilometer. I've just shown the ray path coverage for few representative depth slices. This is 20 kilometer P and S, 60 kilometer P and S, 150 kilometer P and S, and 250 kilometer P and S. So we see that 20 kilometer and 250 kilometer, 20 kilometer, the ray path coverage is more in the Western Himalayas, and the 100 to 50 kilometer ray path coverage is more in the Pamir Hindu Kush region, western syntaxis also. Of course, some part of the salt ranges, but for the other ranges, we have pretty good ray path coverage virtually for the entire area, which means that this ray path coverage tells us which area velocities, estimated velocities will be good, and in which area we can have smaller distances between grid nodes for which you can estimate velocity, and for which areas, for example, in these areas, the grid node separation would be much larger compared to the one that we have used for the position where the ray path coverage is very, very dense. So before we start, I start explaining the results or the tomographic images, one has to be sure about the quality of the results. One of the quality measure is the how the variance reduction is there, or the RMS error reduction has happened because of the inversion. Another way of looking at it is called the resolution. How well the velocity models are resolved. So to do that, one of the standard technique is to carry out horizon checkerboard tests. So here I show three different checkerboard images. These are the input checkerboards. In checkerboard, we put alternate, like if there is a, say, an average velocity at certain depth is obtained from the 1D velocity model, then in checkerboard we'll have alternate addition of 5% or 10% and subtraction of 5% or 10%. So we'll create block model like this. So this is a very extreme kind of model. If our inversion along with the data available works fine for this kind of model, then we are sanguine that okay, the inverted results are reliable. So we have tried different size checkerboards just to find out what is the minimum size of anomaly that can be resolved well. So this one is for 100 by 100 kilometer checkerboard. This is 150 kilometer by 150 kilometer checkerboard, and this is 200 kilometer by 200 kilometer checkerboard for this entire area. So the result shows so for all depth slices, the horizontal slices, we have carried this out. Here we see that this is for the 200 kilometer by 200 kilometer. So what happens is that we see that for the 10 kilometer depth, we do have some amount of smearing of data. So the size of the anomaly that can be estimated should be larger, or there will be some smear. Basically, smearing means averaging of the results from this area to this area. Okay, so there is of course people say that there is a diagonal smearing, but I don't believe in that, because basically you see diagonally we are having same kind of velocity, so there can be continuation of that. But then if this and this have the same kind of color, both red or both blue or both some kind of color, then we say, or this and this have, or this and this have same color, similarly for all other blocks, then we'll say that there is a smearing. So what happens is that yes, we see that some amount of smearing is there in this region for 10 kilometer, 20 kilometer, but 40 kilometer also some amount of smearing we observe here. But then what, considering the fact that this area the station coverage is not very good, so probably that has given rise to this kind of a smearing. But also we would note that even with smearing we do get some values which are, because here the ray paths are going through this area, so it is picking up some information for this particular area. However, the result will be an averaged out result for this particular region. Next, 60 kilometer, 80 kilometer and 100 kilometer depth, we see that the results are much better, and also 150 kilometer, but again some amount of smearing starts around 250 kilometer depth, right? When we use 150 by 150 kilometer blocks, then also we see similar kind of observation we have for both P and S data This is for 10, 20 and 40 kilometer depth, P and S. And again we see that for the 60 to 80 and 100 kilometer results are better, but results are better compared to the shallower depths. But if you compare for the 200 kilometer by 200 kilometer depth, that block sizes, that gave better result. So, but then for 150, 200, 250 kilometer, we see that there is more smearing over here when you are taking 150 by 150 kilometer block size checkerboards, and for 100 to 100.
You are again not audible.
Hello? Hello?
Yes, ma'am.
Now you can hear me?
Yes.
Yes, ma'am.
Shantanu, can you hear me now? Okay. So similarly, we tried for vertical resolution, and the blocks were the depth of about 70 and 170 and 250 kilometer. We kept the boundaries, and this is the vertical input vertical checkerboard, and the resultant inverted results are shown on the left hand side. And what we find is that up to about 150 kilometer, the resolution is good. For example, here you see that there's a difference in blue to yellow, blue, and then red to blue. This kind of variation is observed. But below 170 kilometer, here we have vertical smearing in these regions, and except for the Pamir Hindu Kush region over here, right? So we say that results are good in Northwest Himalayas up to about 150 kilometer depth, and for Pamir Hindu Kush region it's about up to about 250 kilometer depth. The results are good. So this is the checkerboard test is a kind of a very extreme kind of a test. We don't have this kind of anomalies, this box kind of anomalies in real earth situations. So another resolution test was carried out, that is called synthetic modeling with free shape anomalies. So that was also done for horizontal slices and vertical slices. Here we have free shape anomalies. Here we have the violet colored one is the positive anomaly, 10% more than the average value, which is shown in blue color, and brown color is minus 10% variation. These anomaly patterns were picked up from the inverted results. This is for the depth range of 10 to 90 kilometer, and the right hand side shows the input anomaly, free shape anomaly patterns for the Pamir Hindu Kush region, because they from 150 to 200 kilometer depth range. So we have the negative and positive. These were based on what the results we have obtained after inversion. So this is for P and this is for S. So in both cases, the input anomaly pattern was kept the same. And what we see after inversion for synthetic modeling, these are the synthetic models, 10 kilometers, 20 kilometers, 40 kilometers. We do see that with the anomaly patterns, the positive and the negatives, are reasonably well recovered by this particular process for both P and S. Also, we see that 60 kilometer, 80 kilometer, they are quite well resolved. For 100 kilometer, of course, the positive anomalies are very well resolved. The negative anomaly but are resolved in this region. Here we have a little bit of smearing over here, precisely because you see the stations are shown. You can see this small inverted triangles. So we have lack of stations over here. That was one of the problems that was encountered. And for 150, 200 and 250 kilometer depth, we see that the negative and the positive anomalies in the Pamir Hindu Kush region are quite well resolved. Now that we see that from our resolution test, from our reduction in variance, then we are sanguine that okay, whatever we are going to see is reliable and acceptable. So next, of course, sorry, there's another one of synthetic modeling for vertical case. So here we have the negative anomalies and here we have the positive anomalies. These are along the different sections for which we have obtained the inverted. We are going to show the inverted result. We are going to see the inverted results. Okay, so this is the input, and you see that the output shows for the different sections. Section 1 PNS, section 2 PNS, section 3 PNS, and 4, 5, and so on, 4, 5, 6, etc. So what we see is that the results are we are seeing, and they are quite well resolved. So now finally I come to the results of inversion for P and S waves at depth of 10 kilometer, P and S 20 kilometer PNS, 40 kilometer PNS, and in the next slides I will show the deeper ones. So what we see that along the western Himalayan region for up to 40 kilometer at least, we are seeing this negative velocity anomaly for both P as well as S. We are also seeing that kind of negative anomaly for Pamir and part of Hindu Kush also at these depth levels. Okay. And what we see is that in the salt ranges we have a positive anomaly, and in the north of Pamir over here we see a positive anomaly, and then here we see positive anomalies compared to these are relative to the average 1D velocity, because the scale over here you can see is in terms of percentage variation from the average, not the absolute values. And here Delhi Hardwar Ridge also shows up as a positive anomaly zone. Okay. If we go further down 60, 80 and 100 kilometer, then what we see is that negative anomaly for P and S 60 kilometer, 80 kilometer also we are seeing some regions. 100 kilometer along the western Himalayas we see positive anomalies. And when it comes to Pamir Hindu Kush, you see at 60 kilometer both are showing negative anomaly, 80 kilometer also, so very thick, either very thick crust or something is happening there that we got to see, we'll be able to see through the vertical sections. At 100 kilometer Hindu Kush shows as a positive anomaly and the Pamir region still shows up as a negative anomaly. Whereas salt range we still see as mostly positive anomaly, and the Delhi Hardwar Ridge, Indian part of the Indian plate, although I'll not interpret this because this region is not that well resolved, but Delhi Hardwar Ridge is very well resolved. We still see this positive anomaly over here, even up to 100 kilometer depth. So 150, 200 and 250 kilometer, now you see that most part of the western Himalayas we see positive anomalies. So basically what these results indicate, which I'm going to show through the vertical sections, that we have the crustal thickness in the Himalayas it varies somewhere between 50 to 80 kilometers. Even at 80 kilometers in some regions we do see negative anomalies. So basically the low velocity crustal material is observed even up to 50 to 80 kilometers. So there's a lot of variation in crustal thickness along the western Himalayas also. And also we have Pamir Hindu Kush region where we see low velocity anomalies, which is very remarkable, up to even 100 kilometer depth in some zones. Okay. So what happens is that, so if I go forward, now let us have a look at the vertical section. So 11 sections were drawn, 1, 2, 3, 4, parallel to the trend of the Himalayas in this region, and also 5 parallel to this trend, but this is not on the western Himalayas. And then the 6, 7, 8, 9, and 10 are sort of, 9 perpendicular to the trend of the Himalayas, and 11 and 10 and 11 are basically in the north-south direction. So let us have a look at, this is of course the base, the map, just to show the location of the profiles. Okay, so basically you see, look at the P anomaly along section 1, which runs through part of Shivalik and part of Lower Himalayas. What you see is that, so if you, this is the B side, so this is this side and this is A side of section 1. What you see, this is a low velocity zone, pretty thick over here, somewhere between 50 to 80 kilometer thickness you see, and then below that we see the Indian lithospheric, the lithosphere, rest of the lithosphere. Okay, what we see is that it's like it's going like this, and as soon as it comes, because it continues up to here in the Hindu Kush region, where you see that it dips rather steeply in the Hindu Kush region, and the high velocity part of the lithosphere is also seen over here, and it is just not dipping like this, it is also turning in this direction. And this very small dots you see, this is the seismicity over here. Okay, so what you find is that the entire lithosphere suddenly dips at a very steep angle, and in this in the Hindu Kush region, the dip is of course in the apparent dip will be in the northwest direction. I'll call this apparent dip because we do not, this may not be the direction of the true dip. And we have seismicity following more or less, like mostly in the lower velocity part, but almost at the boundary of the high velocity and low velocity part of the lithosphere. Same is true for the section which is slightly north of it, the section 2. Same pattern is also observed, although we are not seeing this turning around, maybe because we are not able to decipher from our data the velocity model below 300, about 250 to 300 kilometers. If you go further north in the section 3, we are also seeing this kind of the plate is going down, subducting. It may not look that steep over here, but it appears like the steepness of dipping is decreasing from 1 to 2 to 3. So next, if we go to the next section, this is section 4. Again, I have plotted over here. Section 4 is over here. Here also you see the same kind of thing. There's a plate going down like this, and the seismicity is occurring between this. The plate contains both low velocity and high velocity. Low velocity on top, so here on this side, and the high velocity material on this side. And then we have seismicity that cuts through the low velocity and high velocity part. So this is anomaly 5, also anomaly pattern 5. Here it is of course going towards Pamir, or maybe it's going to the Pamir region. We could not decipher for a longer profile because of the lack of data over here, and resolution was not good, although it was showing some values over here. So what happened is that we see this dipping layer, part of it over here. Anomaly 6 pattern is going from southwest to northeast through Hindu Kush and Pamir. So here also you see this block, the orientation of, again this is apparent dip, because this is not, this may not be the true dip direction, and you see the low velocity part of the lithosphere and the high velocity part of the lithosphere, and the locations are superposed on this. If it is not the true deep direction, and then the location of the earthquakes could be shown in a different place. So what you see is that again this plate has turned over, like it is dipping and then it is turned over like this. Anomaly 7, of course, now you are away from, we are in the Western Himalayas, away from the Pamir Hindu Kush region, and V part is on this side, so this is northeast direction, and you see that we can see gentle deep of the lithosphere over here. This part is not well resolved, so I'll not interpret this. So gentle deep of the lithosphere over here. Same pattern is also observed for section 8, section 9, and section 10. Right, same pattern of gently dipping or under thrusting of the plates. Along 9, which is the Delhi Hardwar ridge, we observe a very interesting phenomena. This part is where Delhi Hardwar ridge is visible, and then it goes below the Gangetic plain. Ahead of it, what we see, this is well resolved, so I will interpret this result. Ahead of
Yes. So there is some technical glitch in the end of Madam. So please bear with us.
Hello.
Yes, ma'am. You're not audible.
So how far did you hear?
It is now clear.
Okay, so I'll continue. So section 7A, 7-8, which is shown here, 7 and 8, they show because 7A to B, it's going like this. From this is the south west side, this is the north east side. We see under thrusting of the Indian plate below the Himalayas. Section 9 is especially interesting because this is a well-resolved area. This is the Delhi Hardwar ridge. What we see that the Delhi Hardwar ridge is butting against the crustal material in the Himalayas, and over here we see that the crust in this region has buckled up because we interpreted that this is because of ramming effect of the Delhi Hardwar region. I'm not going to discuss section 10, too small for our comfort. So section 11, here it goes in the south to north like this. So south part is like this and north part is like this. What we see is that, of course, we see the under thrusting Himalayan plate, and we also see something over here. So what is that? That is what I'll be discussing in the after the VS anomaly pattern is also discussed. So what we see, these are VS anomaly patterns, that is S-wave velocity anomaly pattern. They more or less follow the trend of the anomaly pattern we see for P wave. So I think I have taken a lot of time, so I'll not discuss them in greater detail. They are very similar. So out of all the 11, I have picked three sections. Section 2, which is like this in northwest southeast direction, 2A, 2B. So what you see is that the Indian mantle part of the lithosphere and the top part of it, it is the crustal part. They are basically subducting below the Hindu Kush region. This is one thing we observe. Second anomaly pattern, because depending on where it is visible much more clearly, it is taken from S anomaly pattern for section C6. Section 6 runs from here to here. So what we see that we do see the crustal material, and we see two subducting slabs. So interpret this as this is from south to southwest to northeast approximately. We interpret this as the Indian mantle lithosphere, and the other one is the Asian mantle lithosphere. So there are several works in this region, because there's a lot of controversy about why there is earthquakes occurring up to about 250-300 kilometers in this region, in Pamir Hindu Kush region. What is going on there? So some people say that only Indian lithosphere is subducted, remnant subducted Indian lithosphere is present here, and some people opine that both remnant subducted Indian mantle part of the lithosphere and Asian lithosphere is present over here. So Asian lithosphere is subducting towards south or southwest, and Indian lithosphere is subducting towards north or northeast kind of a position. 11A also shows the Indian lithosphere subduction and the Asian lithosphere mantle subduction. So this is of course P observation. So based on these observations, we have come to the following conclusion. And one more thing, please note, is that not only in these sections, I forgot to if you look at the crust, the crustal thickness is not constant. Crustal thickness varies not only in the across the Western Himalayas, but along the Western Himalayas also. If we go back and see the VP sections, we see that the crustal thickness is not constant, it kind of varies. And this has been the observation for all the three different parts, the northeastern part, the central part, and this one here, the northwestern part. We have observed that this kind of variation in crustal thickness along the trend of the Himalayas is observed. So in conclusion, what I see is that the top low velocity anomaly, which is imaged up to 80 kilometers. Up to 80 means that somewhere it is around 50, somewhere it is up to 80 kilometer depth. It correlates well with the thicker crust with deeper low density roots under the high mountains in the northwest Himalayas and Pamir Hindu Kush region. What we observe from our tomographic results is that the thickness of the crust varies all along and across the tectonic trend of the northwest Himalayas. Now what happens that across the tectonic trend of north, that is from south to north or southwest to northeast, what we see is that this is well established that the thickness of the crust below the Himalayas increases as we approach from the frontal Himalayan part up to the Tibetan plateau part. This is well established by several workers all along the Himalayas. So this is nothing new. But what we find is that the crustal thickness also varies along the tectonic trend of the Himalayas, and we interpret it that this has happened because there are two hypotheses how Indian plate collided with Eurasia. One hypothesis that it first collided on the westernmost boundary and then it rotated anti-clockwise. Okay, and another hypothesis is that it collided at the central part of the Himalayas, and then of course the rest of the collision occurs. But based on our results that this crustal thickness varies along the tectonic trend of the Himalayas, we propose that the first hypothesis is correct, because what happens, this kind of anti-clockwise rotation will cause thrusting, shortening, buckling, and exhumation during the Indo-Asian collision. Not only that, it will also cause crumpling of the crust along the trend of the Himalayas. This I have not written, but this is what we have found. As if if there's a force, if there's a lateral force also along the tectonic trend of Himalayas, then that will cause crumpling of the Himalayas over here. The Indian lithospheric slab is imaged as a gently under thrusting high velocity anomaly under the northwest Himalayas, and subducted Indian lithospheric slab, which follows the trend of intermediate depth seismicity under the Pamir Hindu Kush region. In the syntaxis zone, sediments are highly fractured fault zones are imaged because there are a lot of faults there. Of course, all along the Himalayas also. These are imaged. This is our interpretation of the low velocity layers also. These are imaged as low velocity zones and rigid hard rocks as high velocity zones. Beneath the Pamir Tianshan, the dipping high velocity anomaly which follows the trend of intermediate depth seismicity represents the remnant of the southward subducted Asian slab. In the southwest of Hindu Kush, the Indian lithospheric slab rolls over, overturns at a depth of 250 km and dips southward. Now, this is something that Kolakov and Sobolev's 2006 paper. They've also suggested that this kind of rolling over of the Indian lithosphere in this region has happened, although their depth ranges are slightly different from ours. The Delhi Hardwar Ridge, imaged as a high velocity structure, is butting against the northwest Himalayas, leading to ramming and locally buckling of the crust therein. Low velocity anomaly attains a very low value near the western syntaxis region. This is attributed to the highly fractured nature of this zone. That is, there are large faults like MFT, MBT, MCT, MMT, MKT, and local scale faults like Kashmir boundary thrust, Pranjal thrust, etc. Now, very low velocity anomaly is also observed at greater depth near western syntaxis. Greater depth means about, like even up to 100 km depth or more than that, which indicate the presence of some fluids due to the metamorphism of rocks at that depth. You see, we have a low velocity, the lithosphere, high velocity lithosphere. On top of it and around it, we also see a low velocity zone. So what is that? That could be because of the presence of fluid due to metamorphism of rocks, or basically presence of continental. Also, it could be presence of continental crust, as suggested that in the 65 to 110 km that we observed in the southeastern Pamir. This is supported by crustal xenoliths that erupted at 11 million year in the southeastern Pamir. That was reported by Tusi et al., Hacker, Gordon et al. Others claim that this represents partially, of course, this 65 to 110 km in the Pamir region. This is one hypothesis that there is a crust, continental crust that has been subducted up to 65 to 110 kilometers. But Kolakov and Sobolev claims that this represents partially molten or hydrated rocks present at such depths. From our work, we cannot differentiate between these two hypotheses, but we can only report that we have a low velocity material in that depth range. This low velocity medium is flanked by a high velocity body on its southeast side, which is the Indian, the mantle part of the Indian lithosphere. Basically, it is a lithospheric material. In my view, in massif in northern Pamir, we see higher velocity, and southern Pamir, where platform sediments and meta sediments are present, we see lower velocity, and which is acceptable, because when we have massive material, high granitic or metamorphic rocks, they will have higher velocity compared to platform sediments and meta sediments. High velocity below 100 km, twice below Hindu Kush and southern Pamir, that represents the subducted Indian lithosphere. Low velocity anomaly northwest and west of it caused by presence of hydrous minerals due to dehydration of downgoing slab. So that brings us to the end of my talk. I hope it's not too long, and thank you very much. And if there's any question, I would take that. Should I go into normal mode, or should I leave it like this? Hello?
Ma'am, you can go to normal mode also, no problem.
You can still see my slides, right?
Yes, yes.
Yes,
Yes.
sir.
Okay, so if you have any,
Dr. Novosity.
Yes.
yes,
Thank you
yes,
so much, madam. Thank you so
you're
much,
most
madam, for such an educative, elaborate, and enlightening talk on the 3D seismic velocity structure of lithosphere beneath Western Himalayas and its geodynamic implications. We
Mhm.
hope all our participants are highly benefited from your lecture. So now, before moving ahead, I would like announce that we will take 3 queries from the attendees. So I request all the participants with a query to kindly raise their hands, and accordingly, we may ask you to unmute yourself to clear your query from the speaker. Thank you.
Right, right.
So now I would like to request our session chairperson, Professor Zia Kail sir, to say a few words on this talk. Over to Professor Kail sir.
Thank you, Navamiti. Thank you so much. Yes, it's a, at the outset, I must congratulate you that it's a really Herculean task, and you have done a tremendous job to image the
Thanks.
3D
Thank,
velocity structure in such complicated region.
yeah.
I had some, some problem in reading your section lines because they are so small letters. Labeling,
Uh,
I could not read them, which is
which
not
ones? Which ones?
miss all, which is north south, which is east west direction. The sections
Yeah.
I could not really individual sections. I could not make out which is
Okay.
one.
Yeah, yeah.
Anyway, but overall glimpse I could have, and at the conclusion also I could make out what you have shown.
Yeah.
One conclusion is that your as you are saying that Indian plate is dipping say north, and then at a depth of something like 250 kilometer it takes a turn and dipping to south. Is that right? Am I correct?
Yeah, that's what I said.
Yes, that's what I think Peslar and Das has reported from Hughes data set,
Yeah.
that the Indian plate takes a turn to the southward dipping turn. So that conclusion is as per the the past studies by Peslar and Das. But
Yes.
in your in another section, I found that you have shown two subducting structure. One is from the in the below Pamir,
Hmm.
which is south dipping structure, and one below Hindu Kush, which is north dipping structure. Am I right?
Yeah, yeah. I mean, I will say exactly north and south, because the orientation of the sections are, because I am not sure, that's what I repeatedly said, but it's more northward and more southward, I would say,
Yeah.
because the sections are northwest, southeast, along the Himalayas.
I
Yes.
understand. Yes, actually, AB is a bit confusing here. Anyway, yeah, you could write with a bit more, larger size, larger capital, alphabet,
Yes, yes.
northeast and southwest. Anyway, your message is clear, and two opposing dipping structure, subtracting structure is well
Yeah,
imaged, and the overturned Indian plate at certain depth, at 250 kilometer, it is taking opposite and opposite to the it is taking deep
yeah,
overturn. So all these messages, I really found this very fascinating lecture, and your imaging is really. I think you have already published this paper, and I would love
yeah,
to have a PDF reprint of this paper. Thank you
right.
so much for really well presented and very informative lecture in this afternoon. Thank you so much. Congratulations to you and to your team. Thank you so much.
Thank you very much. Thanks.
Thank you so much, sir. Now may I request Dr. Debojit Hazarika, sir, to say a few words.
Thank you so much, ma'am, and really congratulations for such an wonderful deliberation of your work. And this is a really excellent piece of work. and really commendable work and excellent image we are able to see even in the entire northwest part of the Himalaya and including that syntaxis zone.
Mhm.
And I'm really thankful that we are able to listen to you. I have read your papers, but now we see that so interesting pictures we are observing here. In your sections, that's I want to know. You may be covering it, but in between I was actually I was disconnected. So in your images, could you find the LAB, lithosphere atmosphere boundary, in the northwest Himalaya?
Can you repeat the question again? I did not get
Yes.
fully.
In your images, because you have shown the images up to about 200 or more than that, 200 kilometers. So, do you see the clear image of lithosphere astronosphere boundary (LAB)?
Well, you know, below the Himalayas, Western Himalayas, I wouldn't say I have seen it because the resolution starts going down as you go. So we have seen up to about 150 kilometer. So I wouldn't say that I have seen the lithosphere astronosphere boundary. And in Pamian Hindu Kush region, you see with all that subducted plates, that's a very disturbed region, and I wouldn't know where the lithosphere astronosphere boundary is. That would be a fascinating piece of work if you can. I think you are working on this receiver function analysis, so if you can determine that from travel time tomography, no, we could not figure that out because our resolution, well resolved area is, as I've said right in the beginning, that below the Himalayas it's about 150 kilometer, and below the Pamian Hindu Kush region it's about 250 kilometer. So you say that 250 kilometer, maybe you should see lithosphere astronosphere boundary, maybe you should, but that's a very Pamian Hindu Kush region is a very disturbed area, and with travel time tomography it would be very, because you see the ray paths as you go deeper, when the ray paths they become more horizontal, so then it becomes a problem of resolution that we are having. So with this kind of work, it is we could not figure out the lithosphere astronosphere boundary. We have found lithosphere astronosphere boundary based on surface wave work, but that's for Bay of Bengal, not for this region.
Yeah, it is really challenging. Even for our receiver function work, it is challenging because the timing of the LAB is superimposed with the crustal reverberation phases. So even
Oh,
the P-wave receiver function, it creates a lot of noise because of the reverberation that is generated within the volume of the crust. And
mm,
so we try for S-wave receiver function, which is because S-wave doesn't produce the multiple after coming the phase. It produces
mm,
multiple before that. So
yeah.
that may be possible that we are also trying. But it is, I was thinking that we could see it through the tomography work. Anyhow, it is very typical kind of signature. It is very difficult to get even for the receiver function approach.
Right.
Thank you so much, ma'am, for this wonderful lecture.
Welcome. Yes.
Thank you so much, sir. Um, Now we have a few query from the audience who have raised their hands. I would like to request Dr. Santanu Pandey from IIG Shillong to please unmute yourself and ask your question. Over to Dr. Santanu Pandey.
Yeah, hello.
Hello.
Yeah, good afternoon. It was really very nice tomographic results I have seen for such a complicated areas such as Pamir and all.
Thank you.
I have just one query regarding the superimposition of the seismicity on the profile of maybe one or two, section 1 or 2 or and the 6, which are basically cutting perpendicularly to each other.
Oh,
In
I
that,
forgot to, sorry, I must interrupt. I forgot to mention that the seismicity that are superimposed on any section or any profile, those are only earthquakes occurring within plus minus 50 kilometer of the section.
yes,
So we have
yes,
not
yes,
taken the entire one. Yes,
yes,
sorry.
yes, yes,
Go
yes.
ahead. Mm.
Basically, my question was that on the northwest, south, east profile line,
Mm.
the seismicity is very well restricted itself closer to the lower velocity sections rather than on the higher velocity. But
Mm.
when you see the north-south section of profile number 6, it is majorly concentrated on the higher velocity part. So can you, which I have very rarely seen or maybe never seen, can you
Uh,
comment on that?
P
That
wave
why
velocity.
P or S? Maybe if you can show the
Hmm.
yes, not
Okay.
this one. Basic. Yeah, 6 P and
Six
yeah,
is, yeah. Okay, I'll go into presentation mode because otherwise, as Professor Kyle said that he could not lead. I understand. I was trying to
yeah,
put too many things together in one slide, so
yes, yes,
that squeezed things up. So basically, let me show the pointer.
yeah,
6A, 6 is going from here to here,
yeah, yeah,
right?
exactly,
So
exactly.
basically what happens is that, sorry. So here, the earthquakes that you see, this is about 300, 400 kilometer from
Yeah,
here. So 6A from here to 400 kilometer will be 1, 2, 3, 4 in this region, right?
yeah, yeah,
So we are plotting the earthquakes around it or
yeah,
superimposing on this particular one.
yeah,
As I have told you that the real dip could be slightly different. This could be the apparent dip that we are seeing. And as a consequence, what may happen, this I have mentioned while I discussed this, that you can see the superposition of the earthquakes. This could be possibly some of these earthquakes are occurring near the low velocity, high velocity boundary, not in
not
the.
exactly.
Uh, so
Yes,
this is basically a problem of superposition. We need to know the actual deep direction, and then based on that we should plot. But then here, the data, like finding the actual deep direction of this bodies is not that easy. We are seeing that Indian plate, whether it is subducting in the northwest direction, is it subducting in this direction? No, somewhere in between, or maybe it is more towards the northwest direction. Possibilities
yeah,
there. So this is a problem of superposition of two different things on top of each other that may
yeah,
have given rise to this problem.
yeah,
Thank you for pointing this out.
yeah. Thanks. Thank you
Mm.
very much for the clarification.
Yeah. Anything else?
Yes, thank you so much. Now we will take our last question. Now may I request Citranjan from Borel Geophysics Research Laboratory to please unmute yourself and ask your query.
Yeah, yes, sir. Now it is audible, sir. Madam,
You are audible, but your voice
yeah,
is very. Yeah.
Madam, actually, I missed some portion of the talk, so a little bit the query is here. So this is only from the this travel time tomography or some this kind of type of tomography.
I could not figure out anything you said. Sorry about that. There's a lot of echo. Can you someone else repeat his question for me?
This is only from the travel time tomography. Yes, madam. Okay.
One of the organizers can repeat the question for him because I'm still not able to.
Otherwise, I will. No, I have my sister having some maybe problem, so I will actually mail to.
Yeah, you can mail it to me, but you can repeat it. He can repeat. I can answer here also if I understand, because I'm not able to understand what you're saying. Sorry about that. Hello? Can one of the organizers repeat his question for me, or he can write to me? I can answer. No problem.
Citranjan, you may try once. Citranjan, you may try once.
Yeah. So, madam, sir, now it is audible, sir. Yeah.
Yes, please
madam,
go ahead.
Actually,
yes.
Yeah, madam. Actually, I missed some portion of the talk. That this is study only from the travel timing tomography or another type of tomography have been added to it.
I'm really sorry, I couldn't get your question. Could one of the organizers Please repeat the question for him to me.
Madam, we are also having the same problem. We could not understand his query. Maybe he'll write to us and I will send it to you, ma'am.
Right. I'll answer. I'm ready to answer anything you ask.
Yes.
Okay.
Thanks.
Yeah.
Thank you so much. With this, we would like to end our question and answer session here, as we have very limited time in our schedule. So I would like to request all the other attendees who have their queries left to kindly email it to us, and we will forward it to our concerned speaker and send their replies to your respective email IDs. Now, I would like to request Ms. Anbesha Dutta Hazarika, a Junior Research Fellow from CSIR and NIST, to deliver the vote of thanks. Over to Ms. Anbesha.
Namaskar and good afternoon to all. As today's event has come to an end, it is my immense pleasure to convey heartfelt thanks to each and everyone on behalf of the entire CSIR NEIST family and the organizing members of IVWGST 2022. I would like to take this opportunity to thank Professor Sagarika Mukhopadhyay from Indian Institute of Technology, Roorkee, for humbly accepting our invitation and delivering such an educative talk. Thank you so much, ma'am, for such a wonderful and edifying lecture. It was a great honor and privilege to have you as a keynote speaker for this event. Our deep sense of gratitude goes to our Honorable Director, Sir, Dr. G. Narahari Shastri, for his tremendous support and guidance in each and every step of this workshop. Our heartfelt appreciation to the international advisor, Professor Andrew J. Michael from USGS, USA, and Professor Daping Zhao from Tohoku University, Japan, and session chairperson, Professor J.R. Kayal, former Deputy Director General of GSI, Geological Survey of India, for their thoughtful insights for these live sessions. I further take this opportunity to express our profound gratitude to the session's co-chairperson, Dr. Debojit Hazarika from Wadia Institute of Himalayan Geology, and Dr. Shantanu Borwa, convener of IVWGST 2022, for his dedication towards this international workshop. A special thanks goes to all the members of Technical and Organizing Committee for their months of hard work and dedication. Last but not the least, I express my deep sense of appreciation to all the attendees for their active participation in today's event, without whom this event would not have been possible. Further, I solicit your continued support during the course of this workshop and look forward to see you all tomorrow for the next and final session of this workshop, which will go live at 3 p.m. Indian Standard Time. Tomorrow, we will begin with a short valedictory session that will begin sharply at 3 p.m. Indian Standard Time. And we heartily invite all of you to this program. And Dr. Mukhopadhyay, ma'am, we hope you will grace us in this program. This valedictory event will be immediately followed by the final lecture session of this workshop. And the keynote speaker for tomorrow's session is Dr. Julian J. Boomer from Imperial College, London, with his lecture on earthquake hazard and risk analysis for natural and induced seismicity towards objective assessments in the face of uncertainty. On this note, we are signing off from today's event. Namaskar, Dhanyabad.
Thank you very much.
Thank you, ma'am.
Thank
you so much.
Thank you, ma'am.
Thank you, ma'am.
You must welcome.
Thank you, sir.
Bye-bye.